So let's go ahead and see if we can go ahead and find a couple linear as well as quadratic approximating polynomials for a given function. And then let's see if we can approximate a specific value using those two approximating polynomials. So let's take a look at this function. Okay, so we have 3 square roots of x, and we're going to center it about where a is equal to 16. And we're going to use a linear approximating polynomial and a quadratic approximating polynomial to be able to approximate this 3 roots of 16.3. All right, so let's get to it. So we go back up and let's remember our formulas. Okay, so these are important to us. And notice in the formulas, we have to find f prime at a and f double prime at a. So let's start by finding the derivative of this original function. Okay, so we know that f of x can be written as 3x to the 1/2, right? The first derivative is going to be equal to 3/2 x to the minus 1/2, which is the same as 3 over 2 roots of x, right? And then f double prime of x is going to be equal to negative 3/4 x to the minus 3/2. Or another way to write that is negative 3 over 4 square roots of x cubed. Now, we're going to substitute 16 back in to all of these values. And then we're going to use those to be able to put together our polynomials. Okay, so our p sub 1 and our p sub 2, which is going to be our linear and quadratic approximating polynomials. Okay, so we can see that f at 16 is going to be 3 roots of 16, or that's going to be 12, 3 times 4. Right? Over here, if we substitute 16 back in for x, that's going to be 3 over 2 roots of 16, or that's going to be 3/8. Right? And then finally, if we were to substitute back in, it's not 16, it's 3/8, excuse me. All right. And then finally, if we were able to substitute back in right here, we're going to find that, and by the way, this is f prime at 16. This is f at 16, all right, which is our a. And then finally, we need f double prime at 16, which is going to be equal to negative 3 over 4 square root of 16 cubed. All right. We know the square root of 16 is 4. 4 cubed is 64. 64 times 4 is 256. So this is going to be negative 3 over 256. All right. And of course, if you don't trust me, you could just throw it into a calculator. All right. So probably be helpful if you guys just have a graphing or scientific calculator available, especially for this, because we are going to be using it quite frequently. And so if I was to just go through and say negative 3 over 4 square roots of 16 to the third, all right, that's going to be negative 0.117. And then we could just convert it into a fraction by clicking this little button. By the way, this is the Desmos scientific calculator. If you do it on your TI calculator, you just hit math, enter, enter, and it'll put it back into some sort of fraction value. All right, so these are the values that we're going to hold on to. Okay, so this is our f double prime at a. We know that this is f prime at a. Okay, so we're going to hold on to that. And this is f at a. Right. So if we wanted to find for part I the linear approximation, I'm going to call that p sub 1 of x. That's equal to, remember, f at a plus f prime at a, x minus a. Okay, and I got that directly from this formula right here. And so if we were to try to find the first degree polynomial, remember that f at a was 12. All right, so I'm just going to have 12 here, plus f prime at a, which was 3/8. And that's x minus 16. Remember, a was 16. All right, so this is going to be our first degree polynomial, okay, P1. All right. Now for P2, here's the good news. For P2, remember our formula is the exact same thing as the linear, okay, except that now we have this other term that we have to deal with the second derivative, okay? And so I'm just going to write it out down here. So this is f at a plus f prime at a, x minus a, plus f double prime at a divided by 2 times x minus a squared, all right? And the good news is we're just going to copy this down when we find P2, all right? That's going to be this stuff. And then we already know that f double prime is 3 over 256. So P sub 2 of x is going to be equal to the 12 plus 3 over 8, x minus 16. And then finally, remember we have negative 3 over 256 divided by 2, x minus a, which is 16 squared, okay? If we wanted to simplify this just a little bit, we could. In fact, we could FOIL everything out, but we're not going to. We're just going to leave it like this. And so finally, we could say that P sub 2 of x is going to be 12 plus 3 over 8, x minus 16, minus 3 over 256 times 2 is going to be 512, and then x minus 16 squared. All right, now the last part of this problem asks us to be able to approximate 3 roots of 16.3. All right, and all we're going to do is we're just going to plug 16.3 back in for x's. All right, so P1, so this is part 3. So P sub 1 at 16.3 is going to be equal to this, except we're going to plug in 16.3 right here. So that's going to be 12 plus 3 over 8 times 16.3 minus 16. All right. And then we could just go ahead and shove that into a calculator and see what we get out of this. All right. So just substituting this back in. All right. We're going to end up with, we solve this, so 12 plus 3 over 8 times the quantity of 16.3 minus 16. All right, and that gives us 12.1125. All right, so that's going to be 12.1125. Now, P sub 2 of 16.3, that's going to be the exact same thing that we just got, except now we're going to have this term that we throw in. So the good news is we can just use the 12.1125 minus 3 over 512 times 16.3 minus 16 squared. And so all we're going to do is just throw that into our calculator. All right, so we're just going to take this value, copy it, and I'm going to subtract 3 over 512 times the quantity of 16.3 minus 16, and then I'm going to square that, and that gives me 12.11197. All right, so that's going to be approximately 12.11197. All right, so let's just hold these two numbers. All right, they're pretty close to one another. Now, remember the original thing that we were trying to approximate, this 3 roots of 16.3, right? Well, if this were 16, that would be 3 times the square root of 16. 3 times 4 would be 12. So the number has to be pretty close to 12. So these look like they make sense, but let's just go ahead and throw in the calculator and see how close we actually get. Okay, so going here. Let's see if I can span this so I can just type in. Okay. And by the way, I didn't ask you to do this, but I'm just showing you how good of approximation that we get just from using the quadratic approximation. Okay, so I'm going to type in 3 square roots of 16.3. All right, and look how close this is. Okay, even for the linear, we get 12.112 and 12.112 if we were to round that 9. But right here, we get 12.111972. And here we get 12.111977. All right, so the quadratic polynomial is really, really close to the value that's given by 3 roots of 16.3. All right, so that's going to be 12.11197, 754. All right, which is really, really close to P2. And again, I didn't ask you to be able to show how close or how far they were apart, but this is just giving you the idea of how powerful just a second degree polynomial can be to be able to approximate one of these sorts of not so nice sorts of values, okay? Now imagine if we had a third degree or fourth degree polynomial, how we would probably get even closer to the value, okay? All right, so this is what the whole idea is of using these approximating polynomials. And this is a power series, okay, of order 2. So in the next video, we're going to take a look at one more of these, and then we're going to take a look later at how do we get higher degree sorts of polynomials.